Mr. Peldon. This is Algebra 2, Chapter 5, Section 1, nth roots and rational exponents. If you have the nth root of x, turn the marker on here. The radical symbol, there's a little swoosh thing there, a little shelf. And the index is n, which tells you which root it is, and the radicand is a thing inside, which you either can do or you can't, hence the can part, right? Because you can't do it just being a decimal answer. Okay, the thing to keep in mind is the definition of a principal nth root has to do with odds and evens. If it's an odd root, you're good to go, because whatever you can put anything you want inside, and you can get pretty much any answer outside. However, if that nth root or the index of n is even, okay, you cannot do negatives. You cannot do negatives. Okay, see, that's not going to work out. Okay, if n is odd or as n is even, when you do the cancellation process of equations, that's going to matter because a radical counts as a grouping symbol. Therefore, there are assumed grouping symbols inside radicals. Therefore, order of operations, grouping symbols happen first. Therefore, if the grouping symbol happens first, this has to be a positive number because it's an nth power. So take any number to a positive power, whether it's 4, 6, 8, 10, whatever you want, the outcome is going to be a positive number, regardless of what the original number was. Okay, if it's odd, doesn't matter because an odd number of negatives is still negative, so it doesn't matter. Okay, the product and quotient rule of radicals is the same for square roots as it is for any root. You can break them together or break them apart. Under the assumption, however, they are the same root. If they are not the same root, the properties don't apply. You can't break them apart and put them together. Okay, let's simplify the following problems. The third root of 64, well, 64 is 8 times 8, which is 2, 2, 2, 2, 2, 2, which is the prime factorization, right? Any number that's a whole number can be broken down into a product of primes, which is the fundamental theorem of arithmetic. You should look that up if you don't know it, the fundamental theorem of arithmetic. So I have a group of 3 here and a group of 3 here, which gives me 2 times 2, because this is the index of 3, which means take out groups of 3. Therefore, my answer is 4. So this is a perfect root because everything came out. So we go to the next one. So this is really, if you think about it, the third root of 2 to the third and 2 to the third, right? So they canceled. Okay, next one, fifth root of 32. Well, if you think about it, 32 is 4 times 8. So 4 times 8, that's the prime factorization. So I have 5 of those. So the answer is 2. Well, no, because this is negative. So I have 5 negatives here. If you multiply 5 negatives, you still get a negative. So the answer is actually negative 2. And if you rewrite it, if you think about it, this is negative 2 to the 5th power, which cancel, right? So the next one, those cancel, leave you with a negative 2. However, these give you a positive 2. And this goes back to the what we said before about the principles of a square root and perfect nth powers. Okay, the inner part happens first. 4 negatives is a positive. 3 negatives is a negative. The odd and even rules apply here. Okay, so each of these cases all the way through are perfect roots because everything comes out. Looking at the next one, however, 24, let's see, that's 3 times 8. So that's 3, 2, 2, 2 is the prime factorization. So I can take out a group of 3, 2 since it's a third root, and I get 2 third roots of 2. So that is a non-perfect root. There's a part left over. Okay, the next one, the fourth root of 8, which is 2, 2, 2, times the fourth root of 2 times 2. Well, neither one of those has 4 of anything. However, I can use the properties, the product rule, and bring them together since they are both the same root. So now I get a 4 here. So that's 2 fourth roots of 2. That's another example of a non-perfect root. Well, fourth root of 81 over 16, that's not going to work out so great, but I can break this up into the fourth root of 81 over the 4th root is 16, which is the 4th root of, let's see, 81 is 9 times 9, so that's 3333, 9 times 9. And 16 is 4 times 4, which is 2222. So I get a group of 2's and a group of 3's, so my answer is 3 over 2. Okay. All right, last one, adding and subtracting. There was a product rule and a quotient rule. There was not an adding or subtracting rule. From kindergarten to college, there is only one rule for adding. You can only add if they are, think about it, like terms. These are not like terms as they sit. I can work on them, though. I can break apart this. Oh, I'm sorry, that's a 3rd root. My mistake. No, I'm misreading that. So that's 5 times the 3rd root of 16, which is 2222, minus 11 3rd roots of 2. So I have a group of 2's out there, so it's 5 times 2 3rd roots of 2 minus 11 3rd roots of 2. So that's 10 3rd roots of 2 minus 11 3rd roots of 2 for a final answer of -1 3rd roots of 2. You can think about why that is. If you had a similar problem of 10x minus 11x, that's just -1x. Okay, same idea, except this is a root, not an x. Pause the video, try the student problems for yourself. Okay, 81, that is 9 times 9, which is 3333. So you have a group of 4, so the answer is just 3. That's a perfect root. 243, let's think about that for a second. Well, 2 plus 4 is 6, plus 3 is 9. Since 2 plus 4 plus 3 is 9, that's divisible by 3, so this is divisible by 3. So that's 3 times 81, because 3 goes into 24 8 times, goes into 3 once. So that's really 3 times, let's see, 81 is 9 times 9, so that's 3333. That gives us 5 3's, doesn't it? For an answer of 3, but this is -3, okay? Because it's really 5 negatives. 5 negatives still make a negative. The next one is -129, because those cancel. This one is 251 positive, because parentheses happen first, because there's always assumed parentheses inside of a radical, whether they're written or not. And an even number of negatives is positive. Okay, let's see, 40. That's what, 4 times 10, so that's 4 times 10. So that gives us a group of 3 2's. That's 2 3rd roots of 5. So that's a non-perfect radical. And the 5th root of 8, which is 2 2 2. That's not going to work out very nicely, because the other one has a group of 5 of them, but I can put them together using the product rule of radicals since they have the same index. 1 2 3 4 5 2's can come out. 4 2 5th roots of 2. This can be broken up using the quotient rule. So 5 5 5 over 3 3 3, because 5 times 5 times 5 is 125. 3 times 3 times 3 is 27. So my answer is 5/3. The last one's an adding and subtracting problem. There's only one rule from kindergarten to college. Are they like terms? So 81 is 9 times 9, so that's 3333. So I can take out a group of 3's for 6 times 3 3rd roots of 3 minus 4 3rd roots of 3. So that's 18 3rd roots of 3 minus 4 3rd roots of 3. They are like terms now. So 18 minus 4 gives me 14 3rd roots of 3. All right, let's go to page 2. So when dealing with roots, there are 6 possible outcomes. I was not really counting 0, because reality is, whether it's odd or even, when you do an nth root of 0, all you're going to get is 0. That's it. Because whether you have an even number of zeros or an odd number of zeros is kind of really irrelevant. Okay. If you try to do an even root of a negative number, right, less than 0, okay, you aren't going to get any real answers. Okay, because you do a root of a negative number, whether that's 2, 4, 6, 8, does not matter. you can't have an even number of negatives. It doesn't work out to negative, correct? However, it is fine for here. You're going to get one real root, and you can rewrite it as a fractional or root form. It doesn't matter. You're only going to get one answer because an odd number of negatives is still negative. That's fine. If you have a positive number and you do an even root, you're going to get plus or minus that answer. So you can write it as radical form or exponent form. Okay, but since an odd number of negatives or an even number of negatives, okay, I'm sorry, this is an even number of positives. I'm sorry, this is positive. I'm sorry. An even number of positives is still positive or negative when you do the plus or minus in an equation. But if it's a negative root, it's still just going to be one answer. Okay, so basically, if it's odd, it's pretty straightforward. You either have 0 or one answer. If it's even, you either have 0, no answer, or plus or minus. Because essentially, at the end of the day, if I have x squared equals 9, x does not equal 3. It's plus or minus 3 when you square root, correct? Because positive 3 or negative 3 squared both equal 9. You don't have to worry about that with odds. The evens is the problem. All right. So if you're going to solve equations, these are the 6 things you need to keep in mind, which is really not 6 if you think about 0. So if I do this problem down here, the third root of negative 216, let's see, 2 plus 1 plus 6, that's 9. That's divisible by 3. So that's 3 times 72. So that's 3 times 3 times, let's see, 3 times 24, because 7 plus 2 is 9. So that's divisible by 3. So that's the third root of 3, 3, 3, 2, 2, 2, right? Because 3 times 8 is 24. So I have a group of 3s and a group of 2s. So that gives me 3 times 2 for an answer of 6. Well, not really. It's going to be negative 6, right? So what I really have here is the third root of negative 6 to the third, because 6 times 6 times 6 is 216. So they really cancel. That's essentially what we have. Okay. Or you can write it this way too, I guess. Negative 6, negative 6, negative 6. Either way. Do the prime factorization using the fundamental theorem of arithmetic, and you'll get it. All right, next one. Fourth root of 16, that's 4 times 4. So that gives us plus or minus 2 since it's an even root. So if you're going to solve an equation, that's what would happen. Okay, in the book you're doing expressions, it'll say assume positive, but equations you're going to have both. Okay, fifth root of 243. So I have, let's see, 2 plus 4 is 6, plus 3 more is 9, so it was by 3, so that's 3 times 81. So that's 9 times 9, so that's 3 times 3 for each 9. So that's 5 of those, so the answer is only 3, since it's an odd root. The next one is even. You can't have an even number of negatives. So there is no real root. Okay, you'll be dealing with imaginaries at that point, but we're not looking for imaginary answers here. And the last one, 12 zeros is still 0, regardless of what you do. All right, pause the video, try the student problems for yourself. Okay, fifth root of a negative, you can have 5 negatives. Let's see, 2 times, let's see, that'd be what, 512 for 1024, which is 2 times 256, excuse me. Half of 512 is 256. Ah, a little messy there. Okay, so 2 times 2, and that's going to be 2 times 128, or 2 times 2 times 2 times 2 times 64. Well, 64 is 8 times 8. So that's 1, 2, 3, 1, 2, 3 for the 8s. So I need groups of 2 here. No, this is fifth root. How did I change halfway through here? I'm sorry. Let's go back and change that. Habit to write 2. Let's go and change that to a 5. I got 5 2s there. 1, 2, 3, 4, 5 2s there. So that's 2 times 2 for an answer of 4. No, it's going to be a negative 4, correct? Okay, because essentially if we rewrite this problem, it's going to be the fifth root of -4 to the fifth. And you can write out 4 -4 or 5 -4s if you want. Either way, right? It cancels. Sixth root of 64. Well, 64 is 8 times 8, so that's 3 2s and 3 2s. For a total of 6 2s, that's plus or minus 2. Since it's an even root, you're going to get both when solving equations with even roots. Seventh root of 343 with C. 3 plus 4 is 7, plus 3 more is 10. It's not divisible by 3. It doesn't end with a 0 or 5. It's not divisible by 5. It doesn't end with an even number. It's not divisible by 2. It is divisible by 7. So that's 7 times 49, which is 7 times 7 times 7. But we don't get 7 of a number, so that's just the answer, right? That's a trick one. It doesn't actually break down. It's approximately 2.302 in the calculator. So it doesn't have a whole number answer. It's a non-perfect one. Okay. What's important here, though, it only has one real root. The next one has no real root. Or no real roots, however you want to say it. Okay. Because this is actually 7i if you actually did it out. It's actually plus or minus 7i, but regardless, the question is not asking for the imaginary answers, though. It only wants the real answers. And the last one is just 0, because 9 zeros, regardless of odd or even, is still 0. And that is the end of part 1.